Okay, this lesson is more on the basics of functions and their graphs. More specifically, we're going to be talking about even and odd functions and their symmetry. Then we'll talk about piecewise defined functions, and lastly we'll finish with a difference quotient on functions. First, we'd like to talk about even and odd functions, their graphs, their symmetry, and how we're going to determine if they're even and odd algebraically. The two types of functions are even functions and odd functions. And we want to take a look at an example of a graph. This is not the only even function and the only odd function, but even functions could possibly look something a little bit like this. Notice that with the even function we have symmetry, and it's symmetric with respect to the y-axis. Okay, another way of thinking about that is that you could fold over the y-axis. The two sides would be kissing or touching. So here's your y-axis. And if I fold it on there, this side on the left would match up to this side on the right, and therefore there is symmetry there. Before we talk about the algebraic determination, let's take a look at what an odd function might look like. Just one example of an odd function would be a graph like this. Odd functions are symmetric with respect to the origin. So what does that mean? Well, it's not just as easy as folding over the y like the even function. In this case, we have to fold over the x-axis and then again over the y-axis. And if you fold over the x-axis and the y-axis, then the two branches would meet up. So over the origin here, notice this branch right here, if I fold it over the x, would come up above the x-axis, and then if I folded it again over the y, then the two branches would meet. And that's the symmetry of an odd function. Now let's take a look at the algebraic determination. If f of x is our function, and we would like to find out if that function is even or odd, the thing that I'm going to do is I'm going to try to find out what f of negative x is, or f of the opposite of x. If f of negative x is equal to f of x for all x in the domain, then we can say that the function is even. What does that mean? Well, when I plug in negative x to the function, if all the signs stay the same, and I'm going to put that here, and all terms stay the same, then the function is even. Now, if I do f of the opposite of x, or f of negative x, and it turns out to be the opposite of f of x, or negative f of x for all x in the domain, then we can say the function is odd. So if I evaluate f at negative x, and all of my terms have the opposite sign, then I know that my function is odd. Now, in some cases, when you take f of negative x, it does not equal f of x, meaning it's even, and it doesn't equal negative f of x, or odd. So some of the signs might be the same, some of them might be different, and in that case the function is neither even nor odd, which is a possibility. Next, we're going to algebraically determine if the following functions are even, odd, or neither. As we said earlier, we're going to evaluate f of the opposite of x in order to determine if this function is even or odd or neither. So every time I see x, I'm going to replace x with the opposite of x. Negative x squared is going to get me x squared. And I'm left with 3x squared plus 1. Next, I would like to compare f of negative x with f of x. Is f of negative x equal to f of x? Well, in this case, yes, 3x squared and 3x squared plus 1 plus 1. everything exactly the same. The signs are all the same, all the terms are the same. So we can say f of the opposite of x is equal to f of x. And if we look above, we remember that if f of x equals f of negative x, then my function is an even function. For the next function, f of x equals 4x cubed minus x, again I'm trying to evaluate at f of negative x. Every time I see an x, I'm going to substitute in negative x. Negative x cubed means negative x times negative x times negative x, which gets me a negative x cubed. Negative times a negative is a positive x, and I'm left with negative 4x cubed plus x. Next, I want you to compare f of negative x with f of x, the original problem. Are all the signs and terms the same? Well, no. Are all the signs different, yet all the terms the same? Well, yes, it is. Negative 4x cubed is the opposite sign of 4x cubed. Positive x is the opposite sign of negative x. Therefore, f of negative x is equal to the opposite of f of x. Every single term has the opposite sign. So that tells us that my function is odd. On our last problem, f of x equals x to the fifth plus 1, I'm going to evaluate at f of negative x. Plug negative x in for every x in the problem. Negative x to the fifth means negative x times negative x times negative x times negative x times negative x. That's 5 times. Because 5 is odd, it keeps its negative value. So f of negative x is equal to negative x to the fifth plus 1. Next, I'd like you to compare f of the negative x with f of x. Are all the terms the same? Yes. Are all the signs the same? Well, we have x to the fifth and negative x to the fifth. That means they're opposite signs, whereas the 1 is the same sign. Do all the signs change? No. Do all the signs stay the same? No. So this function is neither even nor odd. Similarly, we can use possible symmetry to determine whether the graphs are even, odd, or neither. We said that even functions have symmetry with respect to the y-axis. Odd functions have symmetry with respect to the origin. And if it has any other symmetry or no symmetry at all, it would neither be even nor odd. So looking at these 3 graphs, the first graph I can tell has symmetry with respect to the y-axis. If I folded this graph along the y-axis, the yellow part of the graph would meet up with the green part of my graph, and they would be touching. Because we have symmetry with respect to the y-axis, I know that my function is an even function just by looking at the graph. On the second graph, we don't have symmetry with respect to the y-axis. We don't have symmetry with respect to the x-axis either. But if I folded it over the x-axis and the y-axis at the same time, then this yellow part of my graph, when reflected over the x and then reflected over the y, would also be matched up with the green part of my graph. Therefore, I have symmetry with respect to the origin. And if I have symmetry with respect to the origin, I know that my function is odd. On the last example, I have symmetry with respect to the x-axis. Notice that the yellow part of my graph, when folded over the x-axis, would match up with the green part of my graph. So I have symmetry with respect to the x-axis. Well, that's nice that we have symmetry with respect to the x-axis, but I don't have symmetry with the y, I don't have symmetry with origin, therefore I can not be classified as odd or even. I'm neither odd nor even. And if you take a little bit closer look at this graph, you can tell, if you pass a vertical line through it, that it does not pass the vertical line test. This graph is not a function at all. And if it's not a function, then clearly it couldn't be an even or an odd function, because it's not even a function at all. So that's one way to help you out with the symmetry over the respect to the x-axis. You might think, oh, is that even or odd? Well, it's neither, because it's not even a function at all. Okay, next we'd like to talk about piecewise defined functions. A piecewise defined function is a function that is defined by more than one equation over a specified domain. When we talk about piecewise functions, I often like to talk about a cell phone plan or a cell phone example. Let's say if you're planning on buying a cell phone and the company says, well, you're going to have to pay $20 for the first 60 minutes, and then after that you're going to have to pay an additional 40 cents per minute. And then you want to find out how much it's going to cost you to talk for various minutes throughout the month. We have two different categories here. We have one rate if we're talking for just 60 minutes, and we have another rate added on to that if you talk for anything more than 60 minutes. So what we have here is two domains. The first domain is 0 to 60 minutes, the second domain is where t is greater than 60. Any amount of minutes over 60, you're going to have to pay a different rate. You're going to have to pay the $20 plus 40 cents for every additional minute. So let's look at the first plan. If you only speak less than 60 minutes on your monthly plan, you're only required to pay $20. So for the blue function, as long as your time at the end of the month lands between 0 and 60, your fee is going to be $20. But let's say you spoke over 60 minutes, then this blue plan doesn't even come into effect at all. You're going to need to pay $20, plus you're going to have to spend 40 cents, that's a decimal right there, 40 cents for every additional minute over 60. The way we're going to write that is t minus 60. T minus 60 will get you only the additional minutes. For example, if you spoke 65 minutes, 65 minus 60 is equal to 5. That's only the 5 additional minutes that you have to pay for. You don't have to pay for the first 60, so that's why we use the t minus 60 there. Now, if that's a little bit difficult for you, just know that that's not the important part of this lesson. The important part of this lesson is what's going to come next. The important part is to be able to evaluate your function at a given value. For example, I'm trying to find c of 30. Well, first let's discuss what that means. My 30 is the inside of the parentheses, which means it's my t. So I'm talking about 30 minutes worth of talking on my cell phone plan this month. If I'm talking about just 30 minutes, does that belong in this blue function, or does it belong in the red function? Well, the way you determine that is you're going to look at your domain. Does t belong between 0 and 60, or is t greater than 60? In this case, my t is 30, and 30 belongs between 0 and 60, which means it belongs inside my blue function. So if I plug 30 into my blue function, c of 30 is equal to 20. That means I'm going to pay just $20 if I have 30 minutes worth of talking. Next, I'm trying to find c of 120. Well, again, I'm looking to my domain restrictions first. And I've decided that 120 belongs in my red function because 120 is greater than 60. Therefore, I'm going to be using the defined function for the domain t is greater than 60. So 20 plus 0.4 times t minus 60, but instead of t, I'm going to fill in t as 120. 120 minus 60 is 60, which means I'm paying for the additional 60 minutes of talking that I'm doing over. 20 plus 24 gets me 44. So what does this mean? I'm going to be spending $44 on my bill if I speak 120 minutes that month on my phone. Whereas when I'm talking only 30 minutes, I'd only be charged $20 for my bill. What we've done here is we've defined a piecewise defined function, meaning I have two functions for different intervals of my domain, and then I've evaluated at those different intervals. So for your steps here, to find a function value with the piecewise defined function, you must first look for the domain the function value belongs in. Then you substitute that value into the corresponding equation. This is the same thing that we did when we found c of 30 and c of 120. Let's try a few more examples. If I have f of x is equal to 6x minus 1 as long as x is less than 0, or 7x plus 3 if x is greater than or equal to 0, and I'm trying to find some values. I have f of negative 3. Again, the first thing that I said to do is to look for what domain the function belongs in. Negative 3 is my value, and does negative 3 belong less than 0, or is it greater than or equal to 0? Well, in this case, because negative 3 is less than 0, I'm going to be plugging it into the function 6x minus 1. So I plug in my negative 3, and f of negative 3 is equal to negative 18 minus 1, or really negative 19. Notice that I looked at where the 3 belonged in, the domain the 3 belonged in, before I actually determined which equation to plug it in. The next one's a little bit tricky because I'm looking at 0. And my question is 0 less than 0, or is 0 greater than or equal to 0? And the case is that 0 is greater than or equal to 0 because of the equal sign. 0 is equal to 0, therefore I'm plugging it into the second equation, and the second equation is 7x plus 3. So to find f of 0, I replace x with 0, and f of 0 is equal to 3. When I'm trying to find f of 4, please note that 4 is my value. Is 4 less than 0, or is 4 greater than or equal to 0? Well, 4 is greater than or equal to 0, so I'm plugging it into the corresponding equation, 7x plus 3. And my x is 4, so f of 4 is equal to 28 plus 3, or 31. Before we move on, I want you to understand that when you plug in an x value and you're getting out a value at that function, we can rewrite that as an ordered pair. F of negative 3 equals negative 19 can be rewritten as the ordered pair negative 3 comma negative 19. Similarly, because f of 0 equals 3, we are given the ordered pair 0 comma 3. The x is inside the parentheses, comma, the second coordinate is the value at that function. And lastly, if I have f of 4 equals 31, then the corresponding ordered point is 4 comma 31. Let's do one more set of examples here. In this case, for g of x, I have a different type of domain restriction. Notice instead of having it greater than 0 or less than 0 or greater than some value or less than some value, I have it either not equal to 0 or it is equal to 0. So as long as my x value is not equal to 0, I'm going to be plugging it into the first equation. Although if my x value does equal 0, that's the only time that I'm going to be plugging it into my second equation. So looking at g of negative 3, is 3 not equal to 0, or is negative 3 equal to 0? And in this case, negative 3 is not equal to 0, so I'm going to be plugging it in to the first equation. And the first equation says x squared minus 5. But instead of x, I'm going to be replacing with negative 3. After evaluating, I'm getting g of negative 3 is equal to 4. The corresponding point would be negative 3, 4. Next, to find g of 0, I'm asking the question, is 0 not equal to 0, or is 0 equal to 0? I'm trying to find out which domain it belongs in. Well, clearly 0 does equal 0, so I'm going to be using the second equation. So g of 0 is equal to, the second equation is just a number. So when I plug in 0, well, there's no place to plug in 0 for x, so my answer is just g of 0 equals 4. As long as x equals 0, my g of then that value is going to be 4. The corresponding point would be 0, 4. For the last one, I have g of 3. I'd like to determine which domain restriction 3 belongs in. Is 3 not equal to 0, or is 3 equal to 0? Well, 3 is not equal to 0, so therefore I'm going to be using the first equation. G of x equals x squared minus 5. But in this case, I'm plugging in 3 for x. So I have g of 3 is equal to 9 minus 5, or just 4. The corresponding point would be 3, 4.